The question is, could you show us how to calculate internal stresses caused by temperature changes in a 1D rod? You all learned back in physics that if you take a rod and heat it up, it's going to expand, right? This is called the thermal expansion, right? Or if you cool it, it's going to shrink, right? But did you know that temperature changes can increase or decrease the internal stresses in a rod? So let's try to understand the mechanics before we try to calculate these internal stresses. Remember this problem we considered a couple of times in our discussions in previous videos? A segmented 1D rod is held between two fixed points, A and D, and subjected to a couple of external point loads, one at point B and another at point C. We learned that there's a statically indeterminate problem and there's going to be internal forces and therefore internal stresses in each of the segments AB, BC, and CD, right? So in this example, the internal forces are produced by these external forces and of course in conjunction with the boundary conditions, right? Now let's take the same rod but remove the external loads 25 kilonewton and 12 kilonewton. But we're going to heat this up. Let's say the temperature of segment AB increases by delta TAB, temperature of segment BC increases by delta TBC, and CD increases by delta TCD, right? So what will happen? Each segment will try to expand and therefore the overall length of the rod will try to change, try to increase, right? But it can't because we are holding it between two fixed points A and D. So what will happen? Well, forces will develop at the supports, which in turn will lead to internal forces and internal stresses in the rod, right? So this is how temperature changes produces internal stresses in 1D rods. If these temperature changes increases, then the overall length of the rod will try to increase and therefore compressive stresses will develop at the supports, right? On the other hand, if these decreases, then the overall length of the rod will try to decrease and therefore there will be tensile support reactions at points A and D. Either way, there's going to be internal forces in the rod. Here are a few other examples that we considered in some of the earlier videos. But there, the structures were subjected to external forces and we learned how to calculate the internal forces due to them, right? But here, just for emphasis, I remove the external forces and the structures are simply subjected to temperature changes. It doesn't mean that you couldn't have a situation where you have a combined effect of both the external forces and the temperature changes. Most real problems are like that, but here I remove the external forces so that we can focus on the temperature changes. Alright, so in this example 1, we have a gap at point D, but it is fixed at point A, right? The temperature of the segments are changing and therefore the length of each segment is going to change, right? But if point D moves to the right such that the displacement of point D with respect to A due to this thermal effect is greater than delta gap, it cannot do it because we have a fixed point over here and therefore it's going to develop internal forces, right? Remember this wired structure we considered before, right? Supposing, say, due to thermal effect, the length of each wire changes, but the changes are not equal to each other. The constraint is the rigid plate has to remain straight line, right? So what will happen? If these vertical elements are actually made of wires like cables, chains, or ropes, one of the wires will wrinkle up, right? We are not going to have any tensions developing on the wires. Supposing, say, this rigid plate is actually subject to an external force like we had before, then we have a different situation. Then as long as the wires don't wrinkle, then there's going to be some internal forces arising simply from the thermal effects. Similarly, if these vertical elements are actually made of rods like steel bars or something like that, then definitely the thermal effects will have an effect on the internal forces. In other words, temperature changes will lead to the development of internal forces in the vertical elements. In this third example, we have an aluminum core with a brass shell. right? Supposing say this rigid plate is attached to both the brass shell and the aluminum core. This could be achieved either through a nut and bolt connection or through welding, right? Now let's say the temperature of the whole thing changes, then each of these will try to change in length, but the rigid plate is going to try to prevent the differential change in the lengths, right? In other words, the lengths can change, but they have to remain the same, right? So that's going to lead to the development of internal forces. The same situation in this example number 4, where we have a reinforced concrete column. The reinforcements are bonded to the concrete matrix, and if the temperature of the overall system changes, then each part, the concrete matrix and the reinforcements, will try to change in length, but they have to remain the same. The lengths of each of the component will have to remain the same. So that's going to lead to the development of internal forces. We need to know how to calculate thermal expansion or contraction before we can calculate internal forces. So it turns out there is an intrinsic property called thermal expansion or coefficient of thermal expansion that controls this. Just like we had Young's modulus and Poisson ratio controlling the mechanical behavior of materials, here we have the coefficient of thermal expansion. So this is how it goes. Let's say we have a 1D rod that's at a temperature of T1. Now you change the temperature to T2. Supposing say this T2 is an increase from T1, and then we know the rod is going to expand, right? The increase in the length, delta T, due to this thermal effect is given by this equation, alpha times delta T times L naught. And here delta T is the change in temperature, T2 minus T1, and L naught is the initial length of the rod. And this constant alpha is what is known as the coefficient of thermal expansion. Just to understand the units of alpha, let's go through this little analysis I have here. Now rearrange this equation. Alpha is delta T over L naught times delta T, right? So if you were to work out the dimensions of this, delta T, which is the change in length, and therefore it has a dimension of length. L naught is the initial length, and therefore that also has a dimension of length. Delta T is the change in temperature, so it has a dimension of temperature T. This L and L cancels out, so we end up with 1 over T. So use Fahrenheit to measure the temperature in US customary system, or degree of Celsius or degree of Kelvin in SI system. So the units of alpha is going to be 1 over Fahrenheit, degree of Fahrenheit, or 1 over degree of Celsius, or 1 over degree of Kelvin. Now let's take this problem and see if we can find the internal forces and the displacements at the interior points B and C due to temperature increases in the segments A to B, B to C, and C to D. Like we did before, let me first go ahead and define these parameters here. Little FAB is LAB, the length of segment AB, divided by little AAB, which is the cross-sectional area of AB, multiplied by EAB, which is the Young's modulus of AB. FBC and FCD are similarly defined. Now we're going to invoke the principle of superposition and split the problem into a mechanical and a thermal problem. In the mechanical problem, we put this support reaction at point D as an external force on this rod, but we assume that there are no changes in the temperatures. In the thermal problem, we just remove the support reaction dx, but we put the temperature changes for each of the segments. If we add the two, we have the real problem where there is a support reaction dx and the temperatures are changing within each of the segments. Now I'm going to go ahead and calculate the displacement at point D with respect to point A for the mechanical problem and the thermal problem at the two in order to come up with the total displacement at point D with respect to point A for the real problem, right? But the displacement of point D has to be equal to 0. So that is our displacement compatibility condition. And this would allow us to find the support reaction dx And then we can go back and calculate the reaction at point A using equilibrium. So here are some details. So for the first problem, the mechanical problem, first we calculate the internal forces in each of these segments. So NAB prime is the internal forces within segment AB and so on. And you can see NAB prime is going to be exactly equal to dx, right? And of course I'm marking the internal forces as tensions. Tensions are positive. So once we have the internal forces, the deformations of each of these segments are given by this equation. And then you sum up the deformations of each of the segments in order to calculate the displacement of point D with respect to point A. Now here, on the other hand, for the thermal problem, we use the thermal equations to calculate the deformation of each of the segments. So UAB double prime, which is the deformation of segment AB due to the temperature increase delta TAB, is given by this equation. Alpha AB, which is the coefficient of thermal expansion of segment AB, multiplied by delta TAB, which is the change in the temperature of segment AB, multiplied by LAB, which is the length of segment AB. And you have similar equations for UBC double prime and UCD double prime. You sum up the three, you come up with the displacement of point D due to thermal effects. Now the displacement of point D for the real problem is UD prime plus UD double prime. So here's our displacement compatibility condition. U sub D is 0, right? So now this, after substituting all the expressions we had in the previous slide, is going to allow us to calculate a value for dx. So once we have a value for dx, we can kind of go back and calculate everything else we are interested, starting with the internal forces in each of these segments. So this is a real problem, right? So you can see if I section over here, the internal force there is going to be exactly equal to dx, right? Same thing over here and same thing over here. So the internal forces in each of these three segments is actually equal to each other, and that is equal to dx. Now if I'm interested in calculating the displacements of point B and C, we would calculate it like here. The displacement of point B is going to come from the displacement of point B for the mechanical problem and displacement of point B for the thermal problem, right? But the displacement of point B is simply coming from the deformation of segment AB. So that will be U prime AB and U double prime AB. And similar equation for the displacement of point C. So displacement of point C comes from the mechanical and the thermal parts, but the UC prime now come from the deformation of AB and BC. So we have two terms in here and two terms in here. So let's go ahead and pick some numbers for the relevant parameters and go ahead and find the support reaction dx, internal forces, and the displacements at points B and C. So here are the numbers I have selected. You might recognize the values of the Young's modulus and the length from previous problems. You might also recognize that these values go with steel, these values go with aluminum, and these values go with magnesium. Note that I have added a third column here, which is the coefficient of expansion. Let's assume that the temperature increase is the same for all three segments, which is equal to 90 degrees C. So I took the displacement compatibility condition, expanded it, and came up with an expression for dx. Then I went ahead and calculated these coefficients, FAB, FBC, and FCD. We have done this type of calculations before, so I won't spend too much time here. I'm not sure if I pointed it out before or not. These coefficients, little FAB, little FBC, little FCD, are called the flexibility coefficients. These terms are properly defined in matrix structural analysis. It will come up in one of your advanced level structural analysis courses. Then I went ahead and calculated a value for dx. dx is calculated to be minus 64.5 kilonewton. The sign is negative because we marked it as a tensile force, but it has to be a compressive force. That's why we ended up having a negative sign. It makes sense, right? The rod is trying to expand, but the fixed supports at point A and D are not allowing that to happen, and therefore compressive forces develop at the supports. The internal forces in the segments are these. So we see that the same compressive force of 64.5 kilonewton prevailed throughout the rod from A all the way through point D. So here are the details of my calculations for the displacements of points B and C. We have negative values for these displacements, which tells us that points B and C actually move to the left, not to the right. So we answered all the questions. And of course, if you are interested in finding the internal stresses, all you have to do is to take these internal forces and divide them by the respective cross-sectional areas of the segments.